So this is a continuation of Chapter 9, phase diagrams. This will be part 2. And in this part, I'd like to go over 3 of the main things that are asked in terms of calculations on the phase diagram. And they are to identify the phases present. They are to find the composition of each phase that's present and to find the fraction of each phase present. So those are going to be the 3 main questions. And the 2 you want to be very careful of: the composition of the phases versus the fraction of the phases, not to intermix those. It's the biggest error is in giving the wrong one when asked. So the composition of each phase is always worded that way. You might say, I guess, phase compositions. But the key word is composition. Fraction of each phase, it might say, for example, weight fraction. It might say phase fraction or phase amounts. So there's a couple of ways in which that one might get asked. But the idea is how much of each phase do you have, right? And so how much you have is either going to be in terms of a fraction. Do I have 40% alpha and 50 and 60% beta? And that kind of a fraction is calculated based on the weight percents on the phase diagram, and so that's why it's referred to as a weight fraction as well. Phase fraction, phase amounts, again, how much of the phases do we have? It's all about that. 2 is always composition. So that just wants to know how much silver and how much copper, for example, is in each phase. So what is the amount of the components in each phase? And then the first one is we usually don't have much trouble with. That's just reading off the phase that's present at a given composition and temperature. But we're going to go through all 3 of these. And what we'd like to do is go ahead and we're going to look at the nickel-copper system. And perhaps you remember that this is the isomorphous system. So one solid solution, alpha, for all compositions. And we're going to look at 3 different temperatures. All right, so here's the overall copper-nickel phase diagram. And we're going to note that the composition is weight percent nickel. Okay, so if we have to give compositions, we need to make sure that we're giving it in the right percentage. And that means we've got copper all the way over here, and we've got all nickel on that axis. So again, this is the melting point of copper, and this would be the melting point of nickel. And what we're going to go ahead and do is just take a look at this region here on the diagram. So we're going to expand that view so we can see it a little bit better. All right, so there it is. So this region's only going from about 20 to 55 or so. All right, so that is the overall composition is 35 weight percent. So that was given initially in the problem. So we're considering a 35 weight percent nickel alloy. And so that means that 65 weight percent is copper. We really should give both compositions, so I have the full composition amounts. But sometimes we just get lazy and we just write the 1. All right, so the components in this system are copper and nickel, right? 2 sides of the diagram. All right, the phase is present for a 35% nickel alloy at various temperatures. So the temperatures it wants to know first is at 1300 degrees C. All right, so for the phases present, you have to be given temperatures and overall composition. That defines where you are in the phase diagram. So the 35 weight percent just says that we're going to be somewhere on this dotted line. And so now the 1300 degrees C tells me that I'm right here. And so that is in the liquid region, so it's all liquid up here. And so I have then a single phase, and it's just liquid, L. All right, then we drop down to 1250. So at 1250 here, we're at point C, and that one puts us in this region that is alpha plus liquid. So we have a solid solution alpha and a solid solution, a liquid solution L. Okay? Together we have a mixture. And then if we go all the way down to point E, 1190 degrees C, we have all solid alpha. And the microstructure might look something like this, like we're used to seeing. It's a single phase, and we've got some grain boundaries. Okay, so that's the phases present. Next, we want to take a look at the compositions of the phases. So how much copper and how much nickel do we have? So again, we're still at this 35 overall weight percent for the alloy. All right, so let's go ahead and look at case A here again. So 1300 degrees C at 35 weight percent nickel, that's where I am, all liquid. So if I am all liquid, then in single phase therefore, then overall the liquid has to be the same composition then as our overall composition. 35 weight percent nickel, 65 weight percent copper. That's my composition. Then for C, so if we're sitting here at C, then we've got now 2, which said we had alpha plus liquid in the previous case when we just identified what phase is present. And now to figure out how much nickel and copper are in each phase, what we'll do is we're going to draw a line in this region at the temperature that we are at, which let's see, 1250. Right, so we're going to draw a line there, and where it meets these solubility limit lines, it's going to tell us the compositions. Right? And so this one over here is down here at 32. This one over here is down here at 43. Okay. So my liquid, therefore, is 32% nickel plus 68 weight percent copper. And my alpha then is over here at 43 weight percent nickel and 57 weight percent copper. Those are my compositions. All right, let's think about this for a second and see if it makes sense. Think back to the sugar and water example, if you want. Let's say I'm sitting over here, I've got all liquid, and this is weight percent nickel, right? So I'm going to keep adding nickel in, right? So I add some more nickel, and I'm walking across this diagram this way. And keep adding nickel, keep adding nickel, keep adding nickel. Still all liquid, keep adding nickel. Suddenly I hit this line here. This is the liquidus line. If I add any more nickel to it, I enter this two-phase region, right? I already am liquid. So it says I'm going to precipitate out a solid, alpha. Okay, so I've basically reached the solubility limit of the nickel in the copper at 1250 degrees C at this 32 value. So I can keep adding nickel all I want, but I can't get past this. That's the solubility limit. Right? What I do get when I start moving along this axis in here, adding more and more nickel, is I just get more and more of the solid alpha showing up in my slush, my solid and liquid mixture. eventually I'll hit this 43%, and if I keep going, now going to be in, well, if I keep going, I'm just going to continue on with the solid alpha, and in this case, this composition will actually continue to increase. All right, so the liquid then is at 32, and the alpha here is at 43. All right. So those are my two endpoints, and those give me the compositions. All right, let's go to point E here. If we drop the temperature down here to 1190 degrees C, then we're in the all alpha region. So I've got one phase again. If I have one phase, then my composition has to be the same as my overall composition again. So this is 35 weight% nickel. The only time my composition can vary from my overall composition is if I've got more than one phase, and so my components are separated out differently into two phases. Right? But when that's the case, notice that you're always going to have a value that's greater, always have a value that's less than the overall and one that's greater than the overall. Overall, we've got 35. If I have more than one phase, like in this case, then one phase is going to have less than that 35, one's going to have more. And then depending on the fractional amounts of these two different phases, I can average those two numbers to get back to 35. Okay. So we're going to find a way to do that because we'd like to know that particular question is what is the fractional amounts of the liquid in the alpha here at this point C. All right, so that is phase composition, simply giving the amount of two components in each phase present. All right. The other things that are sometimes asked are what is the first solid that's formed when you start from the liquid and you're working your way down. What temperature does the first solid form? And that would be when you hit this liquidus line here. So we just enter into this region that has solid and liquid. So that's at 1260 degrees C. And we could also ask, when does so we're still cooling, when does the last bit of liquid fully solidify? So once I get past 1220, for example, then I'm in my alpha region, I have no more liquid. So 1220 is where my last remaining liquid solidifies. And you could ask these two questions in a similar way if you were to walk up in terms of heating along that line. Then you could say, where does my first liquid form? And then where does my last bit of solid go to liquid? All right. So let's talk about mass fractions or weight fractions. Again, this could also be phase fractions. But how much of this alpha and liquid do I have when I'm sitting here at point C, and I know I've got liquid, I know I've got alpha, and how much of those two do I have in my slush in this case? All right. So first, let's go ahead and take a look at points A and B. Right. So A here, I've got all liquid. So my phase fraction, if I only have one phase, then I've got to have 100%. So my phase fraction is just 1, or you could write 100%, it's fine. And then as we're continuing to drop the temperature, right here at this point B, we still have just 100% liquid. Right? It's only once I cross over this B and move below it that I just start getting some solid to form. So I'm still sitting here, A and B, at 100% liquid. So let's go ahead and move down to D and E. So these are similar. By the time I get to this point D here, I've gotten rid of all the liquid in this region, and I have now just solid alpha. So when I just cross over D, you can see that I'm in the all solid region. And so my fractional amount of alpha at those two different points is again just 1. So it only gets interesting if I'm in a place where I've got more than one phase, like alpha plus liquid at point C, for example. So let's take a look at that. So we're going to take a look at point C. And to do this, what I'm going to do, I'm going to try and be consistent and do this throughout. I think it will really help later, especially when we get into more complicated diagrams. But what I want to do is go ahead and, if I'm at point C and I want to go ahead and draw my tie line. Right, so there I am tracing my tie line, okay, on the diagram. So I've got that traced out here. And I'm also dropping lines down at these endpoints so that I can see what the compositions are on that tie line. Right? And then this one, of course, is my overall, which is still 35 for what we're looking at. So my compositions at this point is what we did last time. Right? So we had a liquid is at 32, a solid at 43, and again I've got 68 copper and 57 copper for this one. All right. So let's go ahead and pull that tie line out of there. Okay. And what I want to do is I want to label the two ends. So the left end of the diagram is hitting my liquid region, so I'm going to go ahead and label it. The right side is it's hitting my solid region alpha, so I want to go ahead and label it. So this tie line now only relates the amounts of liquid and solid alpha that I have. So if this was a more complicated diagram and it had some betas and gammas and other things in it, none of those matter. I'm only in this one region when I look at this. I'm always going to have a point here on my tie line, which is my overall composition of the alloy. So 35 weight percent nickel. So I've got that point. And so now if I look at this tie line, and again, I'm going to label the two ends, so 32 and 43. So I have all the values here for these different points along my tie line. So if I take a look at this tie line, if I was to just measure these two pieces of my tie line on the left and the rights, I would get 0.27 and 0.73 as fractional amounts. Right? So that's the whole tie line there is just 1, and the left side is about 27%, and the right side here is about 73% in terms of those two lengths. So I could do that with a ruler. I could literally take a ruler up here if I traced it just right on my diagram, and I could measure those lengths and compare that to the overall length, and I would get a fraction. Well, these two fractions are the amounts, the weight fractions or the phase fractions, the amount of the two phases I have in this solid. One of them is 73% or 0.73. One of them is 27%, 0.27. So which one's which? So now this is why we call it the inverse lever rule. Okay, so don't forget this term, inverse lever rule. Okay, so what's basically saying is go ahead, and if the liquid is over here on the left, then the right side is my fraction of liquid. The solid alpha is over on the right, so that means my left side then is my alpha. So I'm taking the inverse side, the other side of this tie line. And so that's all you have to remember, and you can grab your weight fractions. And this works for any place in the diagram. Your book's going to have an equation for every possible scenario, and it's just going to be very confusing. Ignore them all. Just draw this one simple tie line in there. Just label the two ends, you figure out the fractional amounts those two pieces make relative to the overall composition, C0 here. And then you remember that it's the inverse rule, so I'm gonna, that piece over there and the liquid over there. All right, that's it. Well, okay, so what do I get to 27 and 73? Well, we have the all the values. So let's just go ahead and do that. So the fractional amount of alpha then, okay, we said is the left piece. So that's 35 minus 32, that's the length. And relative to the entire tie line, which is 43 minus 32. And that's 0.27. And then the, oops, not beta, but liquid is going to be the right side there. So that's 43 minus 35. Right? That's the length. And then the tie line length, 43 minus 32, 0.73. And that's it. And those, of course, have to add to 1, because that's the only 2 phases that I've got. All right, so I hope that's not too bad. So we're going to be doing some more of those, so we'll get used to it, and do them over and over again. Okay, but try on your homework when it's asking you to do these types of things. Try and identify the tie line and pull it out of the diagram, label the endpoints, and then it makes, I think, life a lot more simple. All right, so far, the things that we get asked, so if I have a given composition overall and a given temperature, you should be able to answer what are the phases that are there, what are their compositions or composition if there's only one phase, what is the weight fraction or how much of the phase do I have? Right? Remember, if it's a single phase region, then the weight fraction is just 1. And the composition would just be the overall. All right, sketch microstructures. I haven't really talked about this too much. You can take a look at that in your reading. And if we have any trouble, I can make another short video up on just looking at sketching the microstructure. I will do that later for some of the more complicated systems. And then for a given composition, if I think about cooling, so I'm working from liquid and cooling down, we might ask, what's the temperature that you get the first solid phase, and what's the composition, and what temperature does the last liquid phase become all solid? Now just be careful, because we could always say that we start with all solid, and now I am heating. So all solid, and I'm going to look at heating. Okay, so I've got my solid, now just say it's alpha, and I'm heating up. And so I might ask the temperature where I first get melting, right? So the temperature I first get melting is going to be identical to this one here, temperature at which the last bit of liquid becomes all solid. And then 2, we could ask, what is the temperature of complete melting? When does the last bit of solid disappear and melt? Temperature of complete melting. And that one's going to be the same answer as this question here. All right.